Today we are looking at LeJEPA, a proposed redesign of joint embedding predictive architectures. The big claim is simple but ambitious. Self-supervised models should learn embeddings that are not just predictive across views, but shaped like an isotropic Gaussian cloud. The paper argues that this geometry is not a cosmetic choice. It is a principled target that prevents collapse, improves downstream usefulness, and leads to a much simpler training recipe. Joint embedding methods train an encoder by asking related views of the same data to predict one another in embedding space. That could mean two crops of an image, nearby video frames, or different sensor views. But this prediction task has a dangerous shortcut. The encoder can map everything to the same point or to a tiny subspace and still look predictive. Existing systems fight this with stop gradients, teacher networks, whitening layers, negative samples, and careful tuning. The paper asks a more basic question. If we do not know the downstream tasks in advance, what embedding distribution is safest? The answer they derive is an isotropic Gaussian, a round, evenly spread cloud with no privileged direction. For linear probes, anisotropic embeddings increase bias under regularization and increase estimator variance. In the illustration, the stretched embedding cloud leads to more unstable decision boundaries than the round one. This is not limited to linear evaluation. The paper also analyzes nonlinear probes such as radius-based nearest neighbors and kernel regression. In both cases, the downstream error depends on how the embedding density changes across space. The key quantity is minimized by a Gaussian with equal variance in every direction. So the design principle becomes: make embeddings predictive across views and make their overall distribution look like a standard round Gaussian. To enforce that target distribution, the authors introduce sketched isotropic Gaussian regularization, or SIGREG. Instead of estimating a full high-dimensional distribution directly, SIGREG samples many one-dimensional directions through the embedding space. Along each direction, it compares the projected embeddings to a one-dimensional standard Gaussian. If enough directions match, then the full distribution is constrained toward the desired round Gaussian shape. The statistical framing is important. The method treats distribution matching as a hypothesis test. Are the encoder's embeddings drawn from the target Gaussian or not? Then it reduces the multivariate test to many directional univariate tests. This works because, in principle, a distribution is determined by all of its one-dimensional projections. Practically, SIGREG samples a manageable number of directions and resamples them during training. The paper compares several possible one-dimensional tests. Moment matching is tempting, but finite moments do not identify a distribution, while high moments create unstable gradients. Cumulative distribution tests require sorting, which is awkward for large-scale distributed training. The preferred choice is the EPS-Pulley test based on characteristic functions. It is differentiable, parallel-friendly, has bounded gradients and curvature, and keeps memory and compute linear in batch size. A natural concern is dimensionality. If the embedding has hundreds or thousands of dimensions, how can a few directions be enough? The paper gives two answers. First, neural network embedding distributions are expected to be smooth, so each slice constrains nearby directions. Second, stochastic training resamples directions over time, so the cumulative coverage grows. In experiments, resampling directions beats keeping a large fixed set. LeJEPA combines two terms. The prediction term pulls embeddings of related views toward a shared center, preserving the JEPA idea that different views should agree semantically. The SIGREG term pushes every view's embedding distribution toward the isotropic Gaussian. A single coefficient balances the two. The result removes many familiar heuristics: no teacher-student network, no stop gradient trick, no prototypes, and no complicated anti-collapse machinery. Empirically, LeJEPA is designed to be hard to break. On ImageNet 100, performance stays stable across the loss weight and number of views. Across ImageNet 10 experiments, the method works out of the box across 50 model architectures spanning 8 families. The point is not that every setting is identical, but that the training recipe avoids catastrophic collapse and does not require fragile architecture-specific safeguards. Another striking result is that the training loss becomes informative. In many self-supervised systems, the pre-training loss is a poor guide to downstream quality, so researchers repeatedly evaluate unlabeled tasks. Here, the segreg and prediction losses form smooth trade-off fronts, and the combined LeJEPA loss correlates strongly with linear probe accuracy. With a simple scaling adjustment, the reported Spearman correlation approaches 99% across settings. The headline takeaway is that a theoretically motivated geometry can simplify self-supervised learning. LeJEPA matches or exceeds strong baselines in several transfer and in-domain settings, including small Galaxy 10 pre-training, where it can outperform frontier foundation models transferred from elsewhere. Its representations also show semantic structure. Principal component visualizations separate objects from backgrounds without labels. The broader message is that preventing collapse can be designed into the objective rather than patched on afterward.